Okay, here's the answer key to the quiz. First of all, we have a sled. It's moving on level snow, and so we know that gravity is going to act downwards on the sled, and we know that the normal force of the snow is going to act upwards, and those forces are equal in opposite directions. The force of gravity we label F sub g. The force of the snow acting up we label the normal force. Now in the horizontal direction, we know we have friction. Friction opposes motion, so since it's moving to the right, the friction moves to the left, or acts to the left. But the sled accelerates to the right. So the force to the right, which is a rope, so that's a tension, has got to be larger than the friction force. So in this case here, we have the force of tension pulling to the right. We have a friction force pulling to the left. And the force to the right is clearly larger than the force to the left. So that's a correct free body diagram for that one. For the second one, we have a hockey puck. It's sliding on ice. And so again, we have weight going downwards, and we have a normal force going upwards. We label those F sub n for the normal force, and the gravity force is the weight. And in this case, it's sliding to the right, but friction is the only thing present, and it's moving to the right, so friction acts to the left, and friction is slowing it down. And so there must be a little bit of friction force going to the left here. And the important thing here is that there's no force to the right. There was a force initially to get it moving, but when we observe this, it's sliding to the right, and you don't need a force to keep something in motion. That's Newton's first law. Objects that are in motion will remain in motion. Okay, so now we look at problem number 2. We have an elevator, and it's accelerating upwards. So a free body diagram includes a force going upwards, which, since it's a cable, is tension, and there's a force going downwards. But the force going downwards, which is of course the weight, is not as big as the upwards force because it tells us it's accelerating upwards. So in this case, we know the mass is 200 kilograms, and we know the acceleration is positive 1.00 meters per second squared. So Newton tells us that if we add up all the forces on the elevator, we will get what is called the net force, and the net force will equal the mass times the acceleration. Now, this here means we add up all the forces. So we'll take the forces going up, which is the tension, minus the forces going down, which is gravity. And the difference in those, the unbalanced force, is going to equal m times a. So what we've done is we've applied Newton's law to our problem, and now we have an equation we can solve for the tension. The only problem here is we don't know F sub g, so before we can finish this, we can do this. F sub g, of course, is m times g, which in this case is 200 kilograms times 9.81 meters per second squared. And that equals 1962 newtons. So that's the force of gravity pulling down. So since it's accelerating upwards, the tension must be greater than that. So now we're going to go solve this equation right here. The force of the tension will equal m times a plus the force of gravity. M times a, of course, is the net force, and that equals 200 times 1, or 200 newtons. So the net force is 200 newtons. We add it to the gravity force, which is 1962 newtons, and that gives us the force of the tension in the cable, which equals 2162 newtons, which, if we consider significant figures, is about 2200 newtons. So the idea here is that the net force equals ma, and so I think a lot of you figured out this was 200 newtons, but that's not the answer. That's the unbalanced part of the force. That's how much bigger the tension is than the weight. And so if you know the weight, the force of gravity, the tension's got to be 200 newtons bigger than that, and that's where this comes from. So for problem number 3, we have a cart. This cart is acted on by gravity, and there's a normal force, and those two forces cancel, so we're not really worried about them. What we do care about, though, is that there's two forces on here due to two little engines, and there's a force to the right, we'll call that F of A, and there's a force to the left, we'll call that F of B, and F of B has got to be greater than F of A because the problem tells us the acceleration is to the right at 2.5 meters per second squared. The mass of the cart is 3 kilograms. And we also know that the force to the right, so that's F of B in my diagram, equals 30 newtons. So Newton tells us that if we add up all the forces, that's the unbalanced force, that's going to equal the mass times the acceleration. For this problem, that means we take F of B minus F of A. That's the unbalanced force, the difference between F of B and F of A. That's going to equal the mass times the acceleration. And we wish to solve for this unknown force, F of A. So in this case, we're going to get F of A equals, when I bring this to the other side, bring it to the other side, I'll get F of B minus MA. That's going to be 30 newtons minus the mass, which is 3 kilograms, times the acceleration, which is 2.5 meters per second squared. This is 7.5. 30 minus 7.5 is 22.5 newtons. That's the force that A exerts to the left. And we know it's to the left because we set up our diagram that way, and we said it was to the left in this expression right here because we said minus. So there's that problem. The last problem was a little trickier. You have a bucket. The bucket is being accelerated downwards by the force of gravity, F sub g. There's a tension pulling up, F sub t, and you know the tension pulling up is equal to 30 newtons, but you don't know the mass. We do know the acceleration. The acceleration is 1 meter per second squared, acting downwards, so that's negative. So the idea here is that, first of all, the force of gravity is always going to equal m times g. And we don't know what m is, so we're going to have to solve this problem algebraically. Now we're going to take Newton's law. Newton says when we add up all the forces, we get the mass times the acceleration. The sum of all the forces is going to be the force of the tension minus F of g, and that's going to equal m times a. Let's put in what F of g is. It's m times g. See, F of g is m times g, and that equals m times a. And so now we have built ourselves an equation, and we're going to solve for m, the mass, which occurs twice. So to solve this, I'm going to bring this term to the other side, so I'll get ma plus mg. And then I can factor out the m, and I'll get a plus g. And so if I want to find the mass, m, I can take the force of the tension divided by a plus g, so that's going to be 30 newtons, divided by a was negative 1 meter per second squared, plus g is 9.81 meters per second squared. And when you do all that, you get about 3.4 kilograms. So this is an example of a problem where you have to make an algebraic solution. If you're just plugging in numbers trying to find the force of gravity, you can't solve this problem. You're stuck because you don't know the mass. But if you solve it algebraically, you can combine the mass with the mass there and isolate it and find it.